Hello, this is the Open Enzo, and this is one of my first tutorials about 3D math for 3D games. And this is a fairly basic tutorial on vectors, points, and Cartesian coordinates. So hopefully you guys know that 3D games are made up of 3D objects. And these game engines need to keep track of the position of these 3D objects. Maybe they want to scale these 3D objects. So it's fairly important to know, in my opinion, the math behind these 3D objects. So on a side note, this is a very interesting fact I want to tell you guys, and many of you guys might not know this, but all 3D objects are actually made up of just simple triangles, your regular three vertices. So for example, you have your, let's just say a 3D person game, Metal Gear Solid, and this guy right here is Snake. So this guy, I mean, he's visually stunning and he has all these detailed textures on him, but when it comes down to the basics, he's made up of little triangles put together in a 3D coordinate system, which I will tell you about next, but which forms a mesh. These 3D triangles form a mesh, and then these textures, or for example, his skin is a texture, his clothing is a texture, are put onto those, are mapped onto those triangles to make them look all nice. Anyways, so that was a side note, and let's get on with the tutorial. So first, we have, sorry, new to the software, but yes, we have the coordinate system. So the most widely used coordinate system is a Cartesian coordinate system, and I'm sure, I mean, this is a sort of a recall tutorial, and if you guys don't know this, then I guess a learning tutorial about so this in the 2D world, you guys know that this you guys should know that this is a Cartesian coordinate system in the 2D world where you have an x and a y axis and points are mapped on like this, or this could be a point right here, you know what I mean. So in the 3D world, the Cartesian coordinate system is just the regular xy axis with an added z axis. And points in this plane are usually, you get an x value. For example, you get an x value, and then you get a y value, but then you also have to get a z value, which in some cases comes out of the screen. You can make your z-axis the other way, like that, and keep on going that way. But yeah, my point is that you have three axes in this case, and points are mapped up. For example, you can have a point like which is 3, 2, 3. So it would be somewhat like you have 1, 2, 3, 1, 2. So right here, vector, but then you have 3, 1, 2, 3, comes out like this. So your point is somewhat in, I hope you guys can visualize, but it's somewhat in a 3D space like this. Anyway, so this is your point P. Another one of the coordinate systems used in 3D programming, as I told you guys, this is the most common one used, but there's other ones that exist, and one of the ones is the cylindrical coordinate system, where you have sort of a cylinder going on, and one of the axes runs straight through the middle, and we can call it the h-axis for height. Another axis will be the radial axis, which runs along the radius, and we can call it r. And the third axis, this is sort of confusing for some people because it's actually an angle. The axis is based on an angle, and this angle is the third axis, and we can call it theta, but it's actually the yaw angle. So whatever this angle is, that's how we define these axes. So if it was like a 90-degree angle, it'd be 90 degrees away from the r axis. Anyway, so as I said, this Cartesian one is the most famous, most commonly used axis, but so the cylindrical axis can be used as well. It has its own advantages. So let's check that out. For example, you have a game where you have a pole and you have a ball. it's going to go around like this and slowly decrease the radius due to slowing down of velocity, and it will fall down due it will lower by itself as it rotates due to gravity. And if you think about it, let me just give you a clear view again, actually, sorry. If you think about it, this sort of resembles a cylinder. And wouldn't you rather just use a cylindrical coordinate system to represent that? I mean, I would, if I knew how, but that's why we're learning right now. Okay, so let's move on. Okay, so back to the Cartesian coordinate system. And like I said before, the Cartesian coordinate system had the x, y, and z axes. But I also showed you a generic form which actually sort of looked like this, where the z-axis will look coming out and y-axis going up and x-axis was right here. But the real thing is that these things are all for the programmer's visualization, and they can be mixed up because the math behind this is all the same, as long as you keep it fixed. What I mean by that is that you can actually make the y-axis the z-axis and x-axis the y-axis, or even go something like one axis going this way and one axis going this way and one axis going that way. It's up to you, as long as the math behind it in your game engine is always consistent. Anyways, so that being said, there are two most commonly used systems of the Cartesian coordinate systems, and they're the right-hand Cartesian coordinate system and the left-handed Cartesian coordinate system. And why are they named the right-hand and the left-hand Cartesian coordinate systems? Is because in the right-hand Cartesian coordinate system, the z-axis comes out of the screen. The x-axis stays where it generically is, and the y-axis goes up. And what I mean by is that the positive y goes up and the positive z comes out of the screen. Their negative counterparts are exactly opposite. And why this is called the right-handed coordinate system is when you take your right hand and you curl it around the z-axis, your thumb will point outwards towards the positive z-axis. Whereas on the other hand, in the left-handed coordinate system, the z-axis is actually the same as the positive z-axis is the same as the negative z-axis in the right-hand coordinate system. And it's called the left-hand coordinate system is because in this case, if you take your left hand and curl it around the positive z-axis, your thumb will go towards the positive z-axis. And in this case, it's into the screen. So that's all there is to the right-hand and left-hand coordinate systems. And I'll tell you why we have two coordinate systems. For one, we have this guy. And this guy, the left-hand coordinate systems, I'll give you an example of where we can use the left-hand coordinate system. You can take first-person shooter games, and if you think about it, in first-person shooter games, you're always trying to go into the screen. You want a level, you want an illusion of depth of field to the user. So that's why you want to have the z-axis, positive z-axis going inwards. Whereas I'll let you think this by yourself, where in instances of where we would want the z-axis going outwards. So that's it for the examples of the right hand and left hand axes, and next we're going to cover a little bit of vectors. What is a vector? A vector is something that has magnitude, so in simple words, size, and direction. In contrast to vectors, there are scalars which have magnitude but have no direction. And examples of scalars would be things like mass, how much a person weighs, or maybe something that's confusing is that force, like gravity, is not a scalar because gravity has a magnitude and a direction, but the magnitude of gravity, which is 9.8 grams, is a scalar. Anyways, that was going way off point. So let me describe a vector. A vector has a tail, which is a point, and a vector has a head, which is a point. And in 3D in a 3D world, like a 3D Cartesian plane. The head is a 3D point described by three quantities x1, y1, z1, and similarly this could be x2, y2, z2. And the distance between point 1, the tail, and point 2, the head, is a magnitude, but the direction from this point P1 to P2 is a direction. Hence, so this is a vector, and in the 3D world, I guess I've already defined that. A vector is a triple of scalars, so one scalar in the x direction, one in the y, and one in the z. And compared to a point, vectors can be moved in a 3D world because vectors are just magnitudes and directions, and they could be moved anywhere, whereas points are fixed places. Points are absolute places in the 3D world, whereas vectors are relative. And there are two types of vectors. Points themselves, to represent points, we could have the first type of vector, which is called a position vector. And position vectors, let me get another color here. Position vectors are always, the tail of the position vector starts from the origin, and the head of the position vector can end up anywhere in the 3D world. Hence, this represents a point. Hence these are used to represent points. For example, P3 right here. Whereas the other type of vectors are called directional vectors, and those are the vectors that are usually relative vectors, and they can be moved in a 3D world, and usually objects that need moving, for example, your character, maybe if you're playing a game that involves things like balls, or you want to move it around, usually you want to use relative vectors for that. What else? So in the Cartesian plane, it's good to define this thing called an orthogonal unit vector, and what it is that you have your Cartesian plane, I guess. Just imagine this one right here. A unit vector is a vector of magnitude 1 in the x direction, or the y direction, or the z direction. And these unit vectors are very useful to define while we're actually doing operations on vectors. For example, just a typical way people have been doing this forever is that they define an x unit vector to be I, a y unit vector to be j, and a z unit vector to be k. And what these things actually mean is that we can define a point such as P1, 3, -3, 4 as 3i, hence it's 3 units in the I direction, x directions, minus 3j plus 4k, and that's just the corresponding directions. So, this is I think this should be enough for the basics of vectors, as well as the Cartesian planes and the coordinate system. And in the next tutorial, we're going to cover operations that we can do on these vectors and neat little things called cross products. Thank you for watching.